Hello, my name is Mauricio and I am an aerospace engineering student at the University of Brazil, and I'm presenting here the paper entitled Investigation of a Dual Fuel Hybrid Rocket Engine for Missile and Rocket Applications. Nowadays, many rockets and missiles require a booster and sustainer phases, requiring, in general, two different motors, such as two solid rocket motors, two liquid rocket engines, a solid rocket motor and a liquid rocket engine, or a solid rocket motor and ramjets or turbojet. This increases complexity, costs, and weight. To overcome these issues, a double fuel hybrid rocket engine is proposed in this work, since it provides different regression rates for each of the flight phases, as it can be shown on this figure here. It has a booster fuel grain and a sustainer fuel grain separately, one above the other. So with this solution, a single engine is possible for the whole flight. Of course, there are vehicles which uses liquid rocket engines for both phases or solid rocket motors for both phases, since liquid rocket engines may throttle and solid rocket motors may use different grain geometries. But here in this table it is shown why the hybrid rocket engine was selected. A vehicle which can be used for sounding rocket and missiles has very strict requirements, such as low cost, non-toxicity, non-cryogenic, especially for missiles, low complexity, throttability, non-smoking, especially for missiles as well, and storability. In this table, it is possible to see that the hybrid has the medium levels of performance between the other two technologies. It produces low smoke. It is the safest technology above the others. It has throttability capabilities. It is reignitable. It has a moderate cost, moderate complexity. It is storable. It has low casting complexity compared to solid rocket motors, fuel casting, and has low ambient temperature sensibility. So the propellant must achieve all those requirements I just said. So for the oxidizer, it was selected the nitrous oxide, since it is storable. It is a green propellant with in mixture with the fuels I will talk about right now, and it has low cost. For the booster fuel, it was selected the paraffin, since it is storable, it has low cost, and it has high regression rate due to its liquefying characteristics. Some additives were added to the paraffin to overcome some disadvantages of the paraffins, such as the carbon black and polyethylene to increase mechanical properties, and aluminum to increase performances. And all of those three additives increases melting points of the paraffin. For the sustainer phase fuel, it was selected the HTPB, since it is storable, it has relatively low cost, and it has low regression rate compared to the paraffin. Some additives were added as well for the HTPBs, such as carbon black and aluminum, to increase mechanical properties and performance. Finally, a pressurant was selected to increase tank pressure. The pressurant is helium. For the feeding system, a mass flow control system was implemented to control the oxidizer mass flow rate. A two-phase flow was considered in this equation, which is weighted by a weighting factor K. For the injector, it was analyzed three atomization parameters, such as the Weber number, Onsorge number, and Reynolds number, and those are related in those two pictures here to guarantee the atomization of the injected oxidizer. And the helium is filled in the oxidizer tank, decrease the weight and complexity with the addition of another tank. For the internal ballistic simulation, the chemical equilibrium with applications, or CEAI software, was used to calculate combustion and performance parameters. These both equations here represents an addition term for the thrust coefficient and the specific impulse and characteristic velocity, such as the pressure difference on the exit of the nozzle, a nozzle performance parameter, and a combustion performance parameter. For the burn back, it was used the level set theory using Hamilton-Jacobi equation, like is shown on this figure here, which is a general grain geometry. And the burn back is ruled by the regression rate law, which is showed here beneath the picture, the figure. For the propellant analysis, it was performed simulations varying the percentage of the content of the additives on the fuel grain for both the booster and the sustainer. So these figures here show an example of the content of aluminum on the fuel grain varying with OF ratio for a constant pressure, resulting in a characteristic velocity, which is defined as the chamber pressure times the throat area over the propellant mass flow rate, which is the performance of the combustion chamber. Here it is shown some curves of a fictional anti-ship missile. So here it is possible to see some thrust curves, chamber pressure curves, and characteristic curves. It is easy to understand where the booster phase finishes and where the sustainer phase initiates, since the thrust levels decreases, and since the booster phase it has lower operating time. And here it is possible to evaluate some flow parameters such as oxidizer mass flow rates, mass flux, fuel mass flow rate, or F ratio. Here it is presented a conceptual design of the combustion chamber. So it is possible to see that a impinging injector was selected to increase atomization. A pre-chamber, it is necessary for the atomization and combustion stabilities analysis. A filament wounded composite case was selected to decrease weight. A post chamber, it is necessary for complete combustion. A parabolic bell nozzle was selected to increase performance of the nozzle. A ablative throat insert may be used so when the booster phase finishes, the ablative throat insert vanishes and the optimal throat diameter is reached for the sustainer phase. So it's possible to see as well the booster fill and the sustainer fill, one above the other, the liner and installations, and the igniter. So this work presented a double fuel hybrid rocket engine, which is a promising and possible solution for missions that would require two-stage vehicles using a single rocket engine, reducing complexity, reducing costs, being storable, safe, throttable, reliable, and being no smoke and green propellant. The authors would like to thank the Chemical Propulsion Laboratory of the University of Brasília and the University of Brasília for the support. Thank you.